So I guess I should start. Thank you for coming, even though we have a typhoon and soon probably we have typhoon A. I don't know what's the procedure if in the middle of the class, but let me know if you have concern to go, then you can just simply go. I think the class is a record, so in case you have big concern about your safety, please go. So I guess is today what we're trying to do is to finish the first part of this topic, which is the one sample test. Okay, so this class divided in two parts, one sample test and two sample tests. And I think I want to very quickly review what we have been doing so far, right? To give you a big picture. I guess again I would just resort to the diagram, right? I think a diagram is very useful, right? Just to understand what's going on again, right? The idea is now with population, right? We have something we want to study and we are unable to collect every aspect of it, right? So that's, and we are concerned ourselves with, say, the mu sigma square, right, which is the sample population mean and population variance. And to study it, we try to collect some what we call sample, right, all of it, right? And that is, we're trying to infer the big picture from the small one, right? What we learned from the last topic is we learned that X bar and S are S square a good way to estimate those, right? And in addition, we know that for X bar, we can say more, right? We can say under normality assumption, we can say plus minus M, right? If you know sigma square, right? If you know, and if you don't know, then M would be just Z alpha over 2, sigma over N, right? And this M will be Tn minus 1, alpha over 2, S over root N, okay? These are the ways that you do interval estimate, right? And as we mentioned, these techniques actually are somehow related to what we covered last class, or in particular, let me check in case someone called no class. Hello? No, they just tell me to, I know, I think it's a fake phone. They tell me to compulsory quarantine, but anyway, I don't think it's a fake, real thing. Anyway, so unfortunately we continue the class, okay? So that means that here I have, I said the interval, right? So if this interval, the idea can be extended to what we are talking about this class, this topic is about hypothesis testing, okay? And the idea is we have some claim about, say, mu is equal to some number, okay? And we try to see if the data support what we try to claim, right? Hypothesis means claim, right? We have some claim, okay? And we're going to test this claim, right? And then what kind of claim we are making, right? Just like some manager claims something or product control, which we will make more precise later. But this is a claim and we test the claim. And the idea is related to how these are related to estimation. The idea is being that if, right, we do a interval estimation, right, if it doesn't include the mu, right, it is probably that the claim is wrong. So that is the kind of the overall linkage between the two, right? So that's why we learn estimation and then we learn hypothesis testing. So I hope that is clear what the main thing is about. And so let's review actually the slides. The reason I want to go to slide because I after yesterday class in the other section, so they asked me several questions that I think I put it there. I put in the new slide so that that we fit better. So that's, you can use the old slide, there's no problem. I just add something new there. If you want, you can take the old slide from the blackboard, but otherwise that's the same. I just add more information there to explain. So there's no change in the formula or the definition or what. Okay. So I just reorder a little bit. So the hypothesis testing is basically you are trying to test a claim. If supported is data, the idea is you would try to assume the claim is correct and try to see if the claim is being supported or rejected. Okay. And the null hypothesis is the way that we have a claim on usually population parameters about mean and variance. We call this is a working assumption or prior knowledge, and we denote as X null or X naught. Or alternative hypothesis, which is the claim we would hold if null is rejected. Okay, it will be mutually exclusive with X null, and sometimes it's called X1 or XA. So it depends on what book are you using. And here is the new information I add because someone asked me how do we define hypothesis testing. Okay, so that is the idea is you have a rule, okay, that specify what kind of sample you would go against X null or support X null. Okay, so that means that you will define the rejection region or acceptance region, right? Acceptance region is whether you would not reject X null. Rejection region is you would reject. Okay, and what is critical value is actually the boundary of the rejection region. Okay, so these are the definition of hypothesis testing. I mean, I hope that would help, but I guess it is very clear what we have been doing, but we just do not describe it formally, right? Just basically is they tell a rule. If you see this sample outcome, you will say you reject X null. If you this, you say okay. Okay, so that is what we call hypothesis testing. Okay, so that's a definition, and the boundary we'll call the critical value. Okay, and okay. And we have a simple and composite hypothesis, right? I think that is easy. Simple means you say the parameter equal to a particular value, and composite is say more than one value, right? That means it's interval, right? Less than, equal to, or not equal to, right? So these are the two types. And I said in your class, we focus on simple null and composite alternative. That is easiest thing to do. And it's usually enough for most of the purpose, so that's fine. And the next thing is about the composite alternative hypothesis. Usually they have 3 different ways, right? It's more than, equal to, or not equal to, right? So actually they some kind of hinting what are the rejection region, right? Remember, hypothesis testing, you are specifying what is the acceptance region and rejection region, right? By saying what are the alternative hypothesis, you are telling people what is your rejection region, right? And how do you decide which alternative hypothesis to use will depends on, as I said, what is the what's the consequence, right? If only one sign of the region you think is serious, you only reject in those areas, then that is, right? Just like if you look at a product, right, quality control, you look at harmful substance, if more than a certain level, you violate the law. In that case, you want to use more than, right? Only more than you would ring the bell, right? And if you try to quality control, you want to make sure your main ingredient is no less than certain value, right? Then that is the case where you use the less than, right? So example, because as I think last class in the other section, someone asked me, can we have a example in the business? Yes. So this is the example of a one-side alternative. So consider the case. So this is also a new slide, right? But I mean, everything is already in the old slide, so don't worry about that. Okay. So the example is a local club owner. Okay, and then it's country club, so just like entertaining people. And the worry is whether, because aging society is worried about whether the average age of customer is greater than 45, right? If this is old, then you need to change some entertainment, right? You just need to make it less exciting, more slower, and so on and so forth, right? So in that case, you only take action when the age is large enough. So that means one way to write it is like H now is 45, H1 is more than 45. Okay, so that would be the one way you specify. Okay, and a two-sided hypothesis is you don't know which way would be more serious, or you don't know, actually no idea what's going on. Okay, two-sided is usually the way you want to specify, unless you know you want to reject on one region, right? Because remember, what's alternative is you decide your rejection region, right? So that is your choice. So for example, if you are an auditor, right? The firm claims the mean daily revenue is $3,000. You want to decide whether it's true or not, right? And for auditor, you want to make sure that the claim is exactly right. More than that or less than that is not really good, right? More than that basically is probably a tax evasion, right? Less than that is probably have some problem. You are talking about getting a debt from the bank and so on and so forth, right? So that means that accuracy is important. In that case, you want your alternative to be not equal to, right? Because more than or less than will have a big consequence. Okay, so this example, I hope that can tells you why you would have different, right? Because that to definition hypothesis testing, right? You need to tell people what is a rejection region, right? So that is the idea. And I think I also want to define this because it's also asked by the other class is what actually is the test statistics I mentioned. Usually hypothesis testing, right? We just define what is the rejection region, right? Regarding the data, right? So usually how you would express is in terms of a test statistics, right? You would tell, for example, right? Example would be like this, right? You want to test the population mean, okay? What would be the test statistic is the sample mean, right? Sample mean is help to specify what is the rejection region, right? So test statistic is like you try to tell your hypothesis testing by the test statistics, okay? So you just tell if the statistic is more than a certain number or less than a certain number, you reject, right? So you basically specify your rejection region and acceptance region based on the value of test statistics, okay? An example of such is like, what we will do often is like, look at the population mean, right? And the test statistic sample mean. And you would say, right, if the rejection region is for the null, so for the alternative is bigger than certain number, then you would say, right, the rejection region will be when the sample mean is very large, right? And if you want to reject when mu is very small, right, then the rejection region will be the sample mean is very small, right? When your population mean is not equal to as an alternative, so you would say you reject if the sample mean is very extreme. Is that clear? Is that okay, this one? I think this, we covered it. I think we implicitly defined it already, but I just, because some of you in the other class actually want me to have a formal definition. So I just formally define. Is that okay? So test statistic is a way to represent your hypothesis testing in terms of a number, okay, a function or a random variable, right? Just because the test statistics are random variable, right? It depends on what the depends on the sample you drawn, right? And usually this is sample mean or sample variance, okay? And it's just not, actually we don't use it directly, right? We actually use usually the Z one, you normalize it, right? The test statistics actually use its normalized version of that, right? Or the T, right, is also the one they use, okay? And and I think we define what are the errors right? This alpha is the error that you can commit, right? Basically, this is a sample error, right? Because it's, even though it is true, then now you would be still rejecting it because depend on the sample you drawn, right? So you have to set up the tolerance level, which is alpha, which is called level of significance, right? Even if it's true, we will still be rejecting it, right? So that is the alpha, right? So I hope you still remember that, right? And there's another error, this type of error is if this is wrong, but we fail to reject it, okay? And you can easily see that actually they are closely related, okay? Maybe I just give, because maybe it's good to explain a little bit why they are related. I just give an idea why they're related, right? So suppose I have a mu is here, okay? And that is, suppose I have normality assumption, right? Or central limit theorem. That's what it gives, right? And you can imagine that this is, if this is true, right? If this H0 is set, right? You would be having this bell shape, right? But suppose this is wrong, okay? And suppose the real one is here, okay? And you will still have this guy, right? If this is wrong, okay? And do remember, if you base on the wrong null, right? You would say you reject, say here, right? Suppose you reject here, okay? According to some of your hypothesis testing procedure, you reject here, right? But still, even though this is wrong, okay? And the purple one is true, okay? You will still reject it. You will still not reject it, right? Because it happened if within this, if you get this region, right? You still unable to reject it, right? So you can see that is, I take this one, right? The larger, right? Then I would less likely to reject, right? Because if I'm wrong, if I'm here, right? I would only be able to reject if I end up here, right? Which is given by this probability, right? Only if I only reject, right? If this is true, if this is the case, then I only reject with this probability, right? Okay. And you can see the green and the orange are closely related, right? If I push the orange to the left-hand side, I have bigger green, right? So in some sense, it's like they are closely related, right? Anyway, I guess this is not terribly important, but you just need to know alpha and beta are related, okay? You cannot just simply lower both, okay? The idea is like, if this is not true, maybe somewhere close by is also true, right? So that's why if you don't reject it easily, then you also don't reject the nearby hypothesis easily as well. So that would be the intuition. But anyway, I guess it's not very important. So here I want to say the extra thing I want to say is how do we define p-value? Okay, because I think some of the last class they said, I mean, they spent the weekend to understand what's the p-value. So I think I have to define formally what's the p-value. So p-value can be defined as the lowest significance level that will reject H0. Okay, so just look at the idea what we have said, right? If this is the mu and this is the case, okay, and suppose you reject on the right hand side, okay, you suppose H1 is mu bigger than A, right? Suppose you reject based on this, right? So suppose this is the rejection region, okay, and if the alpha, right? If it's alpha, you change the alpha, then you would just adjust the rejection region, right? So what is the p-value? We'll be just saying that, okay, if this is actually, suppose this is actually your data, right? And this will be your p-value, right? If your actual number is here, this will be your p-value, okay? So it's just like you just figure out what is the lowest significance level that we would reject. right? Just you keep changing the rejection region, right? Because you change the alpha, you keep changing the rejection region, and what's the lowest alpha such that it will be done, right? And that's why, oh sorry, typo here. So that's why people would say this is what we call the observed level of significance, okay, in some case. And the rule, right, simply would be if your p-value is more than the what you pre-specify the significance level, which is like 10%, 5%, or 1%, then you would not reject, right? If this is the case, you would reject, okay? So that is what's meant by p-value, okay? I hope that is clear, okay? But we will go to example again to make sure you're okay, okay? So I just little bit rewrite what we do here, right? There's 3 steps always. First, you state your alternative null, okay? That depends on application, which I think H null is always easy because always simple, right? And the H1 is a little bit difficult because it depends on the question, okay? You read the question, you know whether you need more than or less than, right? And you construct a test statistics, okay? This depends on what kind of thing you're testing, right? You may use Z, Z. If you know the sigma, later you will see if you don't know the sigma, you use T. And at the end of this topic, you may use F, okay, when you compare variance. But today we talk about the T, okay? So we have covered Z last time, okay? And after that, once you construct the test statistics, right? And then either you compare the critical value, right, which is the boundary of rejection region, or you simply look at the p-values, which is the lowest level of significance, right, that you reject, okay? And okay, so that is, you can either compare to that, okay? Now, I guess we would go again to the Z test and then go to T, okay? Because that's the same thing, okay? Almost the same thing. So let's see the Z test again, okay? I do quickly. I just do one left side and both sides, and then I will do the T, okay? So the Z test would be, let me directly go to the example here, okay? So let's review again what's going on. So we'll do this for the T again, okay? So here I have population follow normal, okay? And standard deviation is 4, okay? So I consider simple random sample, okay? And here I have a null which is 6, okay? So if I have this and this, okay? The first thing I can do is I notice this will be true, okay? I'll notice that this X bar, okay? If this is true, you will have a bell curve center at 6, right? Because we claim this is true, right? So remember, hypothesis testing is we assume the null is true, okay? And C is the data supported, okay? So that is the bell curve, okay? Sorry, this should be here, okay? And if we write in this one, okay? We write in this way, okay? What we have is we have the rejection region somewhere here, right? We have some rejection region, okay? If it's more than this, this will reject, okay? And what's the exact value depends on your significance level, right? You put an alpha here, okay? The smaller the alpha, the further away from 6, right? So, and then the problem is actually you want to see if, look at the data, we collect the data, which is 7 and N64, okay? And now you know that because of normal, right? So the variance of this is actually sigma squared over N, right? The variance of this, because bell curve, you need to specify the mean and also the variance, right? So you actually know exactly this one, right? And once I give you this, like alpha is like 5%, right? And the question would be, because it's 7, the question is asking is whether 7 is belong to here or 7 belong to here, right? Or we can look at 7. If 7 is here, we look at the area of this, right? If area of this is more than 5%, then you reject. Sorry, but you don't reject. If less than 5%, reject, right? And the convention is, of course, now this bell curve, you can do it directly, right? There's no problem. But usually that what people would do in general case is, instead of working on this, we transform it to here, okay? Of course, we say it's not necessary to do the transformation, okay? But we do this procedure because we do the same thing with t, okay? The reason why we do this is because this is consistent the way we do t, so that's why we learn this one, okay? So we transform it to z, okay? And 6 becomes 0, okay? Remember how we do the normalization? You minus the mean over the standard error, right? Which is standard deviation of the sample mean, right? So then you transform 7, right? Down there, you become 2, right? That's you minus the mean over the standard error, right? Which is the variance of x bar, okay? And we want to check this area, okay? And this area is what we call the p-value, right? Or observed level of significance, right? And do remember how you figure this out is the, let me use the black color, right? So this is what? This is just the norm as this, sorry, right? 2, true. Remember, this is not the end because this only gives us the area on the left-hand side. So 1 minus. Okay, so you get that, you get this answer. I'm not going to go to Excel. You can just check is the right. And this is less than 5%, then you you reject, right? You reject at 5%, but you don't reject at 1%. You reject at 10%, 5, not 1. Okay. And the other way around is to look at the, as I said, you look at the rejection region, right? The purple color, right? And the limit is called the critical value, right? The boundary, okay? And you try to look at this is actually transform this guy down there, right? You want to make this as alpha, right? And what is this particular value here, right? This value is the right-hand side is 5%, right? That is actually, this guy is actually Z alpha, right? Which is coming from the norm S inward, right? And then right-hand side is 5%, left-hand side is 95, so 0.95, okay? And this will give you this number, okay? Excel. So this number, okay, is the lowest point that you will reject, right? The rejection region. So that's why 2 is more than is inside the rejection region, so we reject. Okay. So I hope by defining the rejection region and the p-value carefully, so I hope you see the both methods are exactly the same. Okay. And probably you ask why I have 2. The reason is the method of critical value is traditionally used when you don't have computer. Right? Because you just need to tell us what are the critical values that we're done, right? So we just need to remember 3 critical values, right? And the p-value require you use calculator to calculate, okay? So which is a little bit more modern, okay? And because of our test, we don't have access to your Excel, so we have to use the old tag, okay? Which is you have to use the critical value method as an unfortunate result, okay? But your assignment or whatever, you can use p-value. Is that clear? Is that okay? Okay. Then I would talk about an 2-sided test. Okay. I'm not talking about the left-hand side. Okay. I'll talk about 2-sided. I'll go to T. Is that okay? Is there anything you want me to say before we go ahead? Because today is a little bit small class, so I can handle questions more efficiently. Okay. Don't worry. If you question, you can still ask during the break. Okay. So I guess we can continue. Now we can continue to do the two-sided one. Okay, just repeat what we are doing. The reason why we are doing this because we do the same for the t. Okay, so let's get started. Okay. Now we have a population follow normal. Okay, and this is 4. Okay, we will drop this assumption. We'll talk about the t. Okay, and we have a sample size of 65 and sample mean of 5, and this mu is 6. Okay, so the first thing you do is you try to see what kind of thing you're doing, right? Because what we have is we have x bar here, okay, and under the null, okay, 6 is in the center, okay, and this is something you expect, right? I think I've drawn so many times. Okay, so the bell shape comes from here, okay, and this is 6, right? This would be n here, right? That would be sigma square over n. Okay, so this is the variance like this. Okay, so here what we have is we are talking about the alternative is this guy, right? Mu is not equal to 6. Okay, so that means that our rejection region is the region where you want to reject the x null will be on both ends, right? Because you would try to say, okay, I'm not happy if the x bar is too big or too small, right? And then usually you make it symmetric, right? And you make a symmetric distance, right? And we will say how you would define the rejection is this area, and this area is what we call alpha over 2, right? This is what we call the level significant. Why? Because remember how we define alpha. Alpha is even this is true, you will still end up in here, right? It's the tolerance level for sampling mistake, right? Remember what's alpha, right? Because even though it's true, it will still end up there, right? But we will say if this is so small, right? We will just say this sample error is so small that we just think this is actually a wrong thing, right? Okay. So, and what we want is to see if 5, we figure out this is the 5 is our sample outcome. So the question is being maybe use red color, right? Where the sample 5, okay, is this 5 is belong to here or belong to here? Okay, is this 5 is which one? Is here or here? Right? If 5 is in the rejection region, then you reject, right? If 5 is outside, you don't. Right? And actually, as I repeat, with normal here, actually we can do it immediately, right? Because you know sigma, you know the sigma square, actually there's a bell curve, so you can be done. Right? You can actually calculate that, right? But as a convention, we don't actually work on the x bar. We normalize it, okay? We just don't do this bell. We will convert it to the standard bell, okay? We'll do it in the z dimension, okay? So that is the standard practice. And later you will see why we do it is because actually we do the same for the t, okay? So that means that we always follow the same procedure, then make our memory easier, okay? So we have that, okay? This 6 become 0, right? And then this value, right? This value, right, will be z alpha over 2, right? And this value will be negative z alpha over 2, okay? And this, of course, is alpha over 2, okay? And we have to calculate where is the 5, okay? 5 turn out to be using this calculation, okay? I think it's very clear. You just subtract the mean and over the variance, right? That is the standard way we have been talking. And turn out this is just -2, okay, somewhere here, okay, -2, okay. And you want to calculate this area, right? And if this area is less than alpha over 2, then you would say you reject, right? Because that's the p-value, right? Because that, remember, what is the p-value is the smallest significance level, right? That you would actually reject it, right? So this, the area of this is just coming from the norm S, this, okay, -2, true, okay? And this area, just the area on the left, but remember you have to multiply by 2 when you compare the p. So this is the p-value. Okay, this is the p-value. And and that's it. And then turn out this value is less than 5%. So you still reject at 5% and 10%, but not 1%. Okay, is that clear? Okay, or we can calculate exactly what is z over 2, right? So this guy would be simply just norm S inwards, okay? Alpha is 5%, alpha over is 2.5%. Okay, so this gives you -1.96. Okay, this will give you -1.96, and which is the critical value, right? Is here, right? So this what the graph shows, right? So your test statistics is within the rejection region, right? So you would reject again. Is that clear what we're talking about? Okay. Is that okay? So don't worry, we are doing the T again, okay? Immediately, okay? So let me do the T again. So the only difference later you will see, the main difference is we here use sigma, we replace by S, okay? And later, instead of Z, we should T and -1, okay? So that will be the two main changes. Of course, we would look at different table, right? But that would be the difference. Okay, so let's directly go to the exercise. Okay, so the reason why we can do this is because of the idea of the T, right? T actually means if we don't know the sigma, right? And then, but this guy will be Tn -1, right? Because if you know, then this is the Z, right? But you don't know, then it's n-1, okay? So that is what you learn from the previous class when we do estimation, right? When we do interval estimation, this is what we learned already, right? Because when you try to do this, right, we just x bar plus minus Tn -1, right? Alpha over 2, right? S over root n, right? So same thing here, right? Just you take the denominator down there, same thing, okay? So we've been doing the same thing here. So let's actually check this out, how we do the left tail, okay? So the right tail first, okay? You can see almost the same thing, okay? Actually the same thing, so I'm not going to go over the slide. Let's actually go to the example, then you will see how we work on it, okay? So here we have a normal assumption, okay? Normality assumption, so this is very important. This is crucial compared to the case of the sigma square, right? Because the sigma square, you can still use central limit theorem, okay? But now you cannot use central limit theorem. You have to make an assumption that we need to verify, okay? And how you verify your data satisfy this? It's very simple. One way to do it is look at your data, you plot a histogram, or then you will see is it look like a bell. If it looks like a bell, then you are no problem. Okay? If the data doesn't look like a bell, then probably you shouldn't use this. Okay? But for our class, it is okay. Okay? It's not that problem. Usually it's not a problem. But I just try to emphasize the importance of assumption here, right? Because it's when you actually go to work, and probably people don't check. Okay? And probably you don't check anyway. But I just need to know that you need to check. And the problem is if the data is not following normal, what you should do, there are many ways. If you learn advanced, that what we call some bootstrap method, There's some method you can do, okay, or some simulation, but that is way beyond our class. So, but just let you know, something not normal can be an issue, in particular for those who want to study finance, right? And financial prices is not really normal, okay, in general. So you have to be very careful when you do this, okay? But anyway, that's way beyond what we're doing because we're doing introductory class, okay? So here we have a random sample of size 16 X bar, okay? Same as before, but now we actually have to rely on the sample variance, okay? So what we have here is we have a null is this guy, okay? So we can still have the same graph, okay? We still same graph, there's no problem, okay? We still have the bell shape, center at 4, okay? We still have the sigma over root n here, okay? The problem is we don't know sigma square, okay? So we can't really work on this one, okay? But still we would have the same idea here. If more than 4, we'll have a rejection region, okay? Like here, right? If this is alpha, okay? And we'll reject here, okay? The main problem is we don't know sigma. We don't actually know what is this guy, okay? What's this guy? Because if I tell the sigma, you know what is this guy, right? What is a critical value, right? And then you can decide if 5 is belong to here or belong to here, right? If belong to the red region, then reject. If don't belong to the red region, you don't reject, right? But what is exactly this question mark? We don't know, right? Without knowing sigma, right? But luckily, the thing we learned from the last class, right? We can actually transform this to the t, right? We actually can, luckily, we can do the t thing, right? This tn minus 1, right? And the good thing is t is also a bell curve, right? It's like a bell, but it's a much fatter bell. If you still recall it's a t, it's like similar to the bell, but have a fatter both tails, right? And the interpretation is similar, right? You still have the bell curve. So that's why everything we learn is can be transported here, right? This is 4 is here, transform, right? And what is this guy, right? This the critical value, which is just t and minus 1 alpha, right? Because here's alpha, right? That's alpha. Okay. And and then question is, what is the green thing here, right? What's the green thing here? The green thing is just 5, right? I don't know which is the right answer, okay? But how can you transform it down, right? You just subtract the mean over the same, but now it's s, right? S over root n, okay? And that is 2, okay? And 2 can be here or 2 can be here. I don't know which one is the right thing. Before I calculate this guy, okay? What's this guy? And this guy will be same as what we do the z, right? Will be just this is just okay. I'll do it later. I'll do the first thing first, right? I just try to do the 2 is the area of the 2 more than 5% or less than 5%. Okay, let me do this first, okay? Because I think I've been doing this first, right? How do you do that? Because it's t, right? So just t, this, okay, 2, true, okay? But you have to subtract from 1. The reason, oh, sorry, I forget to, sorry, I will show it Excel to you soon, but I forgot to put the degree of freedom, which is n-1, okay, true. Okay. So the first thing I subtract from 1 because I calculate the right-hand side area, okay? And this is t distribution, which have t15 because this is 15, okay? And you probably ask why it's 15, but just the way people define the t, okay? We can define t16, but that's how people define the thing. So just n-1. I mean, just the convention we define n-1. And that is how you get the area, okay? and turn out this area is just like 3%. Okay, so less than 5, you reject at 5. Okay, so let me go to the Excel and show you this exactly what we want. Okay, so I want to show exactly this is the case. Okay, so what you do is you subtract 1 because look at the right hand side and T this. Okay, and you have 2 is the value of the test statistics, and you have 16 minus 1, which is 15 because of the sample size. N minus 1, so true. And remember, for continuous, it's always true, right? Because you found the area. Okay, so that is okay. So that is the what we have. That's why 3%, and we would reject at 10%, 5%, but not 1%. Okay, so that is the p-value. Okay, the p-value is so small, right? That is, you are unable to say this outcome coming from sampling error, right? Because by sampling error, it can still be there, but it's so small that we would say, okay, it's unlikely that we can maintain our belief on mu equal to 4. Okay, and the other, as I said, you can look at the critical value, right? Look at what the critical value is, and the critical value, right? It's just same idea. We'll be using inverse, right? It's T inverse, okay? And if the right hand side is 5%, the left hand side is 95%. Okay? So maybe I use the red color. So I just with T inward, okay? 0.95, okay? And this will give us 1.75, okay? Which I will show soon. But clearly, this case is mean the red is it's this case, red is here, okay? And the green is actually this guy. Okay. Okay, 2 is beyond. And the green thing is actually inside the rejection region, so you reject. Okay. So that is it. And I want to show you this, and I show you the T table, then we will have a break. Okay. So let me have finished this one and then have a break. Okay. So T inverse 195. Okay. Okay. Oh, sorry, I forget to put the degree of freedom is 15. So I forget to put 15 here. Sorry. 0.95 and then 15. Okay. So that would be the case you would proceed. Okay. Maybe I have a break first. On a break, I will tell you how to do the T table. I guess that would be, I think it's 3 minutes over. So I just take a break here and we'll resume at 12:30. Okay. So in the meantime, I go around to see if you have any questions. So let me continue. So I just want to show again how to do the T table again. So if this question, how can you find this guy? Okay. And this 15, I want to remind you that's come from 16 minus 1. Okay. And 5% is given by our usual practice. Okay. And if you don't specify what to do, use 5%. Okay. So let's look at the T table. Okay. How do you do a T table? Just look T table. Okay. And let me clean up this thing. Okay. Just randomly pick up this guy. I just pick up this one. And I go bigger. Okay. And this one, right? So this one gives you the tail area. This is exactly the table dimension, right? T alpha. Alpha is the P is alpha here. Alpha is 5%. Okay. And we have 15. So this number 1.753. Okay. So go here. Column 4, right? So row 15. So this guy. So this number. Can you see that? Okay. So that's why we have this number 1.75. Okay. And this is unfortunately the only way you can do for your when doing for a test, right? Unless, as someone claimed, you just unless you print out every single and then you can do it. But I guess the critical value is easier. I mean, in some sense. But of course, you can do the p-value method. Okay. And let me do the other one once more on the left-hand side. So hope that you can know better. Okay. So this P thing, okay, this is the same thing here. We're normal here. We have sample size 12, sample size 16, sample mean 3, S is 2, and mu is 4, okay? And the rejection region is less than 4, okay? So let us actually first draw the diagram here, okay? So let's see here, okay? This is our X bar, okay? Under the null, it will have a mean of 4. Under normal, it will be look like this. Okay. And this is a bell, so that's why it's sigma over n. This is the variance. Okay. And for this bell, and we know we are having mu less than 4. So we will reject if this is when this is very small, right? And how small it is, we define this to be alpha, right? This is determined by what we say the sampling error, right? Even if it's true, it is still end up here, right? And the tolerance level is alpha, right? We design our tolerance level, and usually this is 5%, right? We make a 5% tolerance level as usual, okay? And we want to know this guy, okay? If we know sigma, right, then we're done, right? Because this can be, I mean, this is simply, right, would be just 4 plus, with 4 minus z alpha with 5%, right, would be sigma over root n, right, would be this guy, right? But we actually don't know sigma, so we can't really do it, right? So, then what we're going to do is we look at the other case, we look at the t, right? We can transform this to t15, right? This is t n minus 1, right? And this becomes 0. It is still looks like a bell curve, but much fatter bell. Okay. And again, the same idea is I want it, okay? This guy, okay, is alpha. Okay. And how can you transform here, right? The way to transform is subtract the 4 over s over root n, right? So the question would be, what we want is look at the data is 3. Okay. So we are not sure whether it's here or it's here, right? If 3 is in the red region, then you reject, right? If the 3 is not in the red region, then you don't reject, right? So we need to check out whether it's here or here, right? I don't know. And how can you check, right? If this is negative, this is 3, I don't know it's here or here. I don't know, it's here or here. I don't know which one, right? And the transformation tells us it's -2, okay? I still don't know it's here or there, okay? It's one of the solution, okay? And we want to see if this is small or big, right? When we look at it, is just look at the area, right? If this area is more than alpha or less than alpha, right? That's a straightforward way. Look at the p-value, right? Because look at on the left of the -2 is the p-value, right? So what's the p-value here, right? Is this? How can you calculate this? It's just simply the t, this -2, true. Oh, sorry, you have to forget the 15. 15, true. Okay. So look at t, okay, of -2, and I have n-1. This is n-1. 15 is n-1, right? Is that okay? So let me go to the Excel. Okay, that's t, this -2, 15, true. Okay. So that gives us 3%. So the 3% is less than 5%. Okay, if the 5% is what we decide, then we reject, right? And if we make it 1%, we don't, right? So that's how you get. Is that okay for this one? Now, the other way around to look at this question is what you expect in doing in the exam, right? Is look at this, I don't know, use the red area, right? What's this guy, right? What's the critical value, right? What's the boundary of the rejection region, right? And that is not that difficult, right? It just use the t inward, right? We need 5%, 0.05. The degree of freedom is 15, and that's it. Okay, this should give you -1.753. Okay, so I will show it after I talk about this, right? And this number, right, is the boundary of the rejection region. And turn out your test statistic -2, which is more extreme, right? So it's within the rejection region, so you reject. Is that clear? As I said, I think we repeat enough time. I mean, you should be able to see it. Okay. I hope that's okay. So, I mean, I just convinced you why this is negative. Sorry, why this t inverse is right. So just go to Excel again. So Excel is t dot inverse 0.05 and 15. Okay. So actually, it's the number I claim, -1.75. Okay. So that is the idea. Is it okay? I hope that is clear. Okay. Is there any question? Okay. So let's finally, I do, if no question, I do a two-sided t-test again. Okay. So I have left tail, right tail, and then both tails. Okay. Is that okay? So I do it again, then it shouldn't be an issue. Okay. So here I have the two both tail. Okay. And probably some of you actually asked me during the break is as I'm saying, but how can you know this one, right? In the question or in the exam or assignment, it's very clear that you will be given this one, right? But of course, it's not explicitly write the formula for you, right? But you can infer from the question, right? They want to see whether the consequence, if it doesn't mention, then it's not equal to, right? Or you will try to say, you want to test whether it's equal to or not, right? So that would be usually given in the question. So you don't worry about this. But when you see the assignment, you're very clear, I think. But at the moment, this is given directly to you, but you can easily infer. Okay. So the problem we have is we have X bar again. I'm not going to spend too much time. Justify this is 4 is here, right? So again, this is our problem. We have this, right? And because we don't know, we want to see whether it's 4. Before we collect the data, right? We will say we reject if it is too small compared to 4, too big compared to 4, right? Because we are saying we don't know which side. So any evidence showing that it's too big from 4 or too small from 4, then you reject, right? And how you would assign? You assign alpha of over 2 on the both sides, right? Because anything is too large and too small, you reject, right? And actually, you want to know these two guys, okay? But you can't really pinpoint, as I said, because you don't know sigma, right? If you know sigma, you actually know this 2 point, right? Because it's a bell curve, okay? So the main question now is, now we collect the data, right? Then actually turn out to be 3 is here, okay? I don't know it's here or it's here, okay? I don't know which one, okay? I don't know which one is the actually comes about, okay? If it is in the blue region, then reject, right? If not, then not, right? Or I can look at the area on the left of 3, right? Look at this area, the black area. If the black area is compared to alpha over 2, right? If it is less than alpha over 2, then you reject, right? The same thing, right? So it doesn't really matter which way you use it, okay? So I think it's rather clear that we don't work on this X bar. The reason is because we don't know sigma, right? So that means that we have to look at the T, okay? And we use, because N is 16, so we use T15. Okay? And you can transform here to here, right? By subtracting the mean, right? Over S or N, right? So 4 minus 4 will become 0, right? That's how you transform 4 to 0, right? The reason is 4 minus 4, right? And that will look like this, right? A bell curve, okay? And the question is, first is, what is 3 here, okay? And 3 here actually turned out to be -2, okay? We don't know which one, okay? But that is how you transform -4 over S over root N, right? So that is the transformation. And now we can do the p-value method, right? As I said, you calculate the area, right? This area, okay? Asking is this area big or small, okay? And remember, we compare alpha over 2, okay? So for simplicity, the p-value we just multiply by 2, right? Because the difference of p-value is the smallest, okay, significance level that you reject, right? So, and So that is how we define. So how to define that? Okay, that would be T, okay, this -2, 15, true. Okay. Do remember is you compare alpha 2, so you multiply by 2. Right? So that's why 2 times this. Okay. So just to remind yourself, the p-value have to be multiplied by 2 when you calculate area, because you don't know which side, so that's why you have to multiply by 2 by the rule, right? Because so turn out this is more than 5%. Okay. So I'll show you the Excel afterward. Okay. But that means that if you use 5%, you can't reject now. Okay. You actually can reject at the one tail, right? The same question. But now become a two tail, you really can't reject. Okay. So we can't reject in the two tail one. And if you're 10%, you still can reject. Okay. Now the 5% become a thing here. Okay. So let me show you this next cell. Okay. So to make sure that I convince. So is that okay, or you have any question? I mean, we're not in a hurry, so any question? Okay. So the other way around is look at instead of looking at the purple one, look at the because we also want to ask the question, right? What is the blue one, right? What's the blue one? Okay, the blue one was alpha 2 here, right? And so this number, right, and this number, they're symmetry, right? So this number is actually t negative t 15 0.025, right? Because 5%, right? So 2.5% on both sides, right? T 15 0.025 here, okay? And this will be just t dot inverse, okay? 0.025 15. Okay. And of course, this guy will be t dot inward 0.975 15. But you just need to find one because they're symmetric. Right? So let me do the first one. Okay. The t dot inverse 0.025 15. Okay. Okay. Or you can put t dot inward 0.975 15. Okay. So it's 2.13. Okay. So in this case, it's actually okay. The blue one is actually negative 2.13. Okay. So you notice that this is actually the case is here. Okay, this is the case. Okay, this actually is the case. Okay, not this guy. Okay. So that's why you can't reject at the 5% certificate level. Is that okay? Is there any question? Just wait a little bit. If a question, please feel free to raise your hand because today we have a relatively small class size. Any question? Because from now on, we only talk about two tail tests, okay? And one tail will be the same thing, okay? We're not going to repeat this left tail, right tail, two tail, okay? We always talk about two tail, okay? And the one tail, you know the procedure, you know how to do it, okay? We're not going to repeat every test we have 3 times we do, okay? We just do, that is, we always do two tail, okay? when we illustrate the result. Okay. In your mind, I think you can know how to do one tail. Okay. Is that a question? Now, before we conclude the one sample test, I think it's good to look at the special case we call binary data. Okay, is that okay for this one? So binary data, what we have is, instead of talking about sample mean, we talk about sample proportion, right? So that would be the next slide. Okay. So with sample proportion, okay. And remember, okay, if we have n pi bigger than 5 and n1 minus pi bigger than 5, okay, then the central limit theorem applies. Okay, we can approximate the sample proportion is actually normal. Okay, so the only difference you can see here compared to this case, if you recall, right, in the normal case, right, we will make assumption on mu, right? We will say we make on mu, right? We will say mu equal to A as your H naught, right? X0, right? Is the assumption. And making assumption on the mu have nothing impact on sigma square, right? Because mu and sigma square are disconnected in general case. But for binary data, once you make assumption on the sample population proportion, which is the pi, okay, we make assumption on that, you automatically get one thing for free because the variance is this guy, right? Remember, this is what we have said, right? So that's why for proportion, you don't need to worry about the t. There's not about t. It's always set because this is by it's the good thing about proportion binary data is you got the variance for free. You don't need to estimate that. Is that clear? So that is the that's what we're going to do. Okay. So the only difference, let me emphasize again, is you got the variance for free because when you assume the mean, which is the population proportion, you said equal to A, the variance automatically fixed for you. Okay, you fix the mean, you fix the variance. Okay, or fix the sample error, right? In that sense. Okay. So let's see. Okay. Okay. And as I said, I focus on the case of two-sided and one-sided. I think you know how to do it. Okay. So let's see the example. Okay, we have a binary data. Okay, and remember, binary data means the data is either 0 or 1. Okay? The 0 or 1. And with a random sample of size 50, okay, and sample proportion of 0.5, okay, and pi, and the population proportion is 0.4 and not equal to 0.4, it's two-sided, okay. So it's claiming that certain thing is proportion is 40%, okay. And the first thing you want to check again is you would just have do this, right? We will have a p here, right? Paste the row, it's a random variable, right? And it's centered at 0.4 under the null. Okay, this is coming from this guy. Okay. And because of you can first check is n pi more than 5 and n1 minus pi more than 5. Is it true? Yes, it's true, right? N pi is more than 5, right? And 1 minus pi also more than 5. Okay. So that means that I can draw a bell curve. Okay, I can draw a bell curve. Okay, this is allowed. Okay, and the variance is given by 1 minus p. Sorry, it's assumed is 0.4. The variance is given by this, right? 1 minus 4, 1 over 1 minus over 4, and over n. Okay, and n is going to be 50, right? So I just okay. So actually, I know the bell curve. I know everything, right? So it's a bell curve. I know the variance, right? So I know I don't need to go to t, right? So what if here is a two-sided one? So you reject, right? If okay, it's belong to this region, right? And this region I put it, the area is alpha over 2, okay? And actually you can calculate these two guys, right? The reason you can calculate these two guys is because this is actually normal. You know the variance, you know exactly everything there, okay? And but as the way we actually work, we would just transform it to the z, right? Just to make everything same as what we have done, right? So that's z here, okay? And you transform this becomes 0, right? Just normalize, right? You just subtract, right? Because this, right? Because the bell here, right? This guy is a bell, right? 0. So this is just z alpha over 2, right? It's negative z alpha over 2, right? Okay. And what you want to see if what you figure out is this is I think on 5, okay? Or I don't know, is here or is here, okay? There's something to be determined, okay? And what you're going to do is to transform this 0.5 down there, right? And you go to 0.5, actually turn out you do this calculation, right? I hope that is clear why this is the case, why this is, because this is 0.4, 1 minus 0.4 over n, right? So this two guy is 1.44, okay? Right, so we want to calculate, now we calculate this, we're going to calculate this area, that's the p-value. When you times 2 is the p-value, right? So you want to calculate the area on the right-hand side, 1.44, and then multiply by 2, then that's the p-value, right? So you want to calculate this as 2 times normal, right? It's norm s, okay, not just 2, so I had to subtract, okay? Normal this, okay? 1.44, true, okay? But this only gives us the left-hand side, so you need to subtract 1. That gives you the right-hand side, okay? And then you multiply by 2, will give you the p-value, okay? Let me repeat the statement here. I need to subtract from 1 because I need to look at the right area. And I multiply by 2 because I calculate the p-value, which is the 2 times of the area in the 2-tailed test. If it's 1-tailed, then just multiply by 2. Okay? So turn out to be 15%. So you can't actually reject using 5%, 10%, 1%. And let me show you, this is the formula. This is 14% in Excel. Okay? It's 2 times 1 minus norm dot s dot this 1.44, true. Okay. So that is the number. As I mentioned, is 14% or 15%, as you like. Okay. So you really can't reject this guy, right? So 0.5 is still the reasonable range here. Is that okay? Is that clear? And and I think it's easy to see alpha over 2 is 1.96. Okay, I'm not going to repeat it, but I just write down the formula, how you get this, right? This 2, right? I think it's very clear how we do this. Norm S inward 0.025 for the left-hand side. The right-hand side will be norm S inward 0.975. Okay, and that will give you a value around 2, right? So that's why sometimes we call rule of thumb is 2, right? Look at people talk about the rule of thumb is 2. If the test statistic is more than 2, right, in absolute value, then you reject, right? So that would be usually the rule of thumb. Is that a question? Because we're done with all one sample tests. Is there any question? Of course, we talk about the two sample. We preview that, but before we end, is there any question? Because this is a rather small crowd today. If you have questions, just feel free to raise, I guess. Don't worry. I mean, after that, we're almost done today. So we'll just give you a very gentle preview what we're doing. Not going to be heavy anything, okay? So this is the last calculation we're doing, okay? I will just give you a more brief overview of what we are doing in the next class. Is there any question? Is that okay? Any further question? Any question? Okay. If no, then I start talking about two sample. Okay. So far we have one sample. Okay, and then we compare the sample mean to some values. Right. That is very useful. Right. As I said, I mean, you look at whether the mean is claimed by a certain value. That is very useful. Okay. But sometimes you actually would have two different samples to compare, right? You look at how we do. Maybe I can just, I think you are done with this. I may show you this one. Okay. So far we focus on one population, right? We look at the sample and then we just do the calculation test whether the mu is equal to a certain number. Okay. And someone may ask, how do you compare sigma equal to certain? Yeah. And that would have a chi-square test, which is beyond our class. But anyway, so what we are doing, a two sample here means the following. We have a population 1, and we have another population 2. Okay. So in your mind, what's this here? You can imagine population 1 is a bunch of girls. Okay. And population 2 is a boy. Okay. And or 1 is customer in one city, 2 is customer in the other city. Right. So what do you care in this framework? Right. In the one sample test, we're able to measure the mean of population 1, right? And you can also measure the variance of population 1, right? And you also may be able to evaluate the population mean for population 2, the variance of population 2, okay? So the question is, very often we care about the difference between the two mean, right? What we care is actually sometimes get the difference. Okay, this is the thing we care, sometimes called delta mu. Okay, why we care about this? Why I care about delta mu? The reason is being that, say, 1 is the population, say, have vaccine, right? 2 have no vaccine. You care about people with vaccine and no vaccine, how likely to get the disease, right? Mu is the average rate of getting disease, right? Or you get the vaccine, how many days you take to recover if you have the disease, right? So this is comparing performance, is why you want to care about this, right? You compare performance of two things, right? Suppose population 1 is a shop on the online shops. Population 2 is the sales from the offline, right? You want to care whether the offline is selling more than online, right? Because you want to see whether you want to put money on advertising on the online store offline, right? Or you want to see if you are having an advertisement, say, suppose you hire a idol like Mirror to advertise your good, right? And population 1 is the sales data with the advertising, 2 is without. You want to see if spending the money is worth it, right? So that is the idea, right? You compare performance of the two. Okay, so we will study two different cases. Okay, here there's a case 1 and case 2. Okay, case 1 is where sigma 1 square is sigma 2 square. Okay, so the case where the variance the same. Okay, and you may ask, how can we make sure the same? But you can just say you are doing by simple random. We are doing the treatment randomly, so then you can make this assumption, right? And of course, a more general case is you can't make this assumption. You have to make this more generic case. Not equal. Okay, if they're not equal, that's how we do. So that's the two cases we want to study. Okay, so that's the two tests we'll cover in the next class. Okay, so this is the first thing we want to see if actually we want to test with the 0 or not, right? In particular, we'll see whether the difference between the two treatments, right? And or the example, if you are looking at is like your Netflix, right? Or video streaming company, you want to see if women are using the service more than men, right? Why you care? Because say, suppose women like to watch romantic movie and men want to watch scientific movie, right? If the difference, then you decide what kind of movie or film want to buy, right? So it's very natural thing to do, right? Because you look at the make decision, right? You see what to see their actual difference, right? Because they must be different, but you want to see their actual difference enough, right, to justify an action, right? Because you always collect data, right? It is possible that men more than women, women more than men, but doesn't mean that you need to take action, right? You need to check it out whether actually they're different enough to justify a different action. Okay, so that is the goal. Okay, the first two goals. The third goal we are doing is the first goal is looking at is these two populations are paired. Okay, go back to the idea about boys and girls. Okay, pair means that girl number 1, okay, is related to the boy number 1. Okay, and girl number 2 is related to boy number 2. Okay, and girl number 3 is related to boy number 3. Okay, and what we actually care is not average, the difference between the average. Okay, what we care because now we have no the data, right? So I have the data of the girl number 1 will be denoted by x1 1. Okay, girl number 2 I will denote by x1 2. So 1 is the group. Number 3 will be x1 3, and the boy number 1 will be x2 1. Boy number 2 will be x2 2. Boy number 3 will be x2 3. Okay, so instead of looking at the original data, I care about the difference. D1 is x1 1 minus x2 1. So basically the first girl minus the first boy. D2 will be x1 2 minus x2 2. The difference between the second couples, right? D3 is asking the x1 3 minus x2 3. Okay, so we want to check mu of D is 0 or not. Okay, asking if the difference. Okay, and you ask why actually do this. Actually, this is actually what the science was doing. Why? Population 1 is the things before treatment. Okay, and population 2 is the thing after treatment. Okay, say you often see this advertising, right? One you look at the medicine for reducing mass, right? One is I have a very big tummy, okay? Two is I take the medicine, the tummy becomes smaller, right? So you look at the guy before they take medicine, look at the tummy size of the medicine, you take the tummy size, right? You want to see the difference. Is it going to reduce, going to be useful? Right? There's a lot of this, right? Someone take the bicep, become very big, right? Or the hair, no hair before, after you have hair. Okay? How can you show your medicine have useful? Right? You have the control experiment. You have the same guy before have the medicine. This is the length of the hair, right? Afterward, you have the hair, the length of the hair afterward, right? Or you have the before you have a big tummy, now you have no tummy, and you want to see whether see or not. So this is the case 3. Is that clear what case 3 is? Okay, it's what we call, this is exactly what the science is doing. It's a control experiment. There's a treatment there, right? Before and after. Okay, basically it's a kind of before and after idea. Right? It's like before after. Right? The treatment here. Okay. And or this is very useful when you talk about the program, right? Talk about when a company, they do the marketing, right? They want to buy a TV advertising, right? And you try to see the TV advertising is helping, right? You just look at each store before they do advertisement, after they do advertisement. You take a difference and see whether better or not. Okay. Now, and I want to mention the last 2 exercise is we have case 4. Okay. Case 4 is very simple. Case 4 is just talking about binary data. Binary data for case, we talk about case 2. Okay. Case 2 is compare the mean. Okay. But I now compare 2 proportion. Okay, it's very simple, right? We just have a population 1. I want to see how many people like mirror, okay, among the girls. And look at the boys, how many people like mirror. I want to see whether is it boy like mirror more than girls. That's it. Is that clear? Is that okay? So just binary data become pi 1 compared to pi 2. Okay, is it pi 1 minus pi 2 minus this, right? This is our action now. Okay. Is that okay? So this is a 4 scenario. And last, I mentioned the last scenario, okay, case 5. Okay. Case 5 is actually the case we're talking about actually is underlying this guy. We want to see if the variance of group 1 is same as variance of group 2. Okay, just check the variance. And probably you ask why we care about the equality of the 2 variants. Okay, why we care about this? First, there will be interest to compare variance, right? By definition, right? Because you can tell us which case you want to use. And second, variance, okay, is a measure of how good a model is. Okay, let me go to the next slide, and I hope. I mean, I don't need the next slide. Okay, so put it this way, right? Variance is looking at how good things are, right? How variation of things are, right? So basically, what you do is compare this is comparing how a model, mathematical model, it works, right? So you have 2 different model 1, model 2. Maybe I have a slide. Okay. So what I see is I have model 1, model 2. Okay. And model 1, model 2 can be some mathematical model. Okay. And if you put in some data inside, okay, okay, and the model actually gives some prediction, right? So some input, some output, right? Some prediction here, okay? And you could to some prediction, you have something correct, right? It's right. and you're something wrong, right? Because there's some prediction you're right, there's some prediction you're wrong, right? Prediction wrong, okay? And you want to check the variance of these two, or wrong, actually we call error, right? Actually error, okay? And we want to compare the variance of two errors, okay? And if the same, then these two models are similar, right? If one model has a lower variance, then the model is better, okay? And this, why we care about this? This is what we are doing for the last two topics. When we talk about ANOVA or regression, okay, the last two topics is talking about we make a model, okay? A model means we have some way to describe this data, okay? And we think that the data generated in this way and make some prediction, and the prediction can be right or wrong, right? It's whether we fit or not, right? If it's a good fit, then you have the error will be very small. If not so fit, error is big, right? And how do you compare the two? Look at the variance, okay? And that's why the F test, which we call, will be used a lot of time after the F test. This is what F test. You compare the error, but this will be taught at the next week, okay? So we'll cover this next week, okay? So there will be 5 different more tests, which we'll cover next week, okay? So don't worry, all these things are just preview, okay? So I hope you have a nice day. I mean, stay safe. Yes, okay, have a good day.